Hello friends. In this video we are going to learn about the role of Gilman reagent in organic synthesis. Gilman reagent is the organocuprate compound discovered by an American chemist, Henry Gilman, in 1952. Its synthesis may look easy, but doing practically required high skill in handling air and moisture-sensitive reactions. To prepare Gilman reagent, first alkyl halide is treated with Li metal in dry ether or THF solvent at 0 degrees Celsius to form alkyl lithium, which when treated with cuprous iodide to form lithium dialkyl-cuparate Gilman reagent. On dissolving in diethyl ether, this lithium diorganocuprate reagent is expected to exist in a dimeric, 8-membered ring form. Gilman reagent is usually employed in 3 kinds of reactions. In the first one, conjugate addition, it acts as an alkylating agent on treatment with a β-unsaturated carbonyl compound and known to give the 1,4-addition product. Secondly, it is used in the regioselective epoxide or aziridine ring-opening reactions. And thirdly, it is used in preparing alkane in Koi-Howe synthesis where it reacts with primary or secondary alkyl halides or tosylate symmetrical and unsymmetrical alkanes. Gilman reagent reacts with primary or secondary alkyl halides to give alkane by replacing the halogen atom. But this is not SN2 substitution reaction. Soon you will understand why. This Gilman reagent gives symmetrical alkane when treated with the same alkyl halide and gives unsymmetrical alkane when treated with a different alkyl halide, and this reaction is called Koi-Howe synthesis. It is interesting to see that it reacts with vinyl halides to give an alkene. Now you must be wondering that vinyl halides does not undergo nucleophilic substitution reaction because it is sp2 carbon. But here it is reacting with the Gilman reagent. This clearly implies that this reaction does not follow the nucleophilic substitution pathway. The possible mechanism for this reaction is that organocuparates first undergo oxidative addition with alkyl halides and the reductive elimination give the final product. It could be similar to Ullmann reaction. This reason also explains the reaction of aryl iodide with Gilman reagent. I hope it is clear to you now. Let's move forward. Reaction with acid chlorides. This reagent does not react with many polar unsaturation groups such as nitro, nitriles, esters, and ketones, making it useful for converting the acid chlorides into ketones chemoselectively. Gamma ketoester can also be prepared by this reagent. Reaction with aldehydes and ketones. Organocuprate react with aldehydes to give a mixture of diastereomers in the case of an alpha chiral center, scheme 7. Generally, it does not easily react with ketones, but exceptions can be there that we are not going to discuss here. Another significant use of the Gilman reagent, which makes it unique among all organometallic reagents, is that it is widely used to introduce the alkyl group at the beta position of alpha β-unsaturated carbonyl compounds. In example 9, there is a methyl group above the plane which hindered the attack of alkyl anion of Gilman reagent from the same side. Therefore, the attack takes place from below the plane. In example 10, there is an alkyl chain at alpha position with leaving group. Therefore, negative charge of enolate attack further to give 5-membered ring. 4. Double alkylation. It is important to trap the enolate anion by adding another alkyl halide in the same reaction pot before proceeding with hydrolysis. Reaction with epoxide aziridine. Epoxide ring opening takes place from the less hindered side to give the more substituted alcohol. Significant use of Gilman reagent in natural product synthesis. The following examples involved 1,4 addition of Gilman reagents to prepare the precursors of various natural products. In this slide you can see the examples involving epoxide ring opening by Gilman reagents. You can pause this video to see these interesting chemical transformations. Thank you very much for watching this video. I hope you have found it useful and unique.